Firstly, I'll like to thank the organizers for replacing a potentially much more interesting speaker. Did not turn up by me. Okay, so what's the topic? So let me pose the question that we are trying to address in this talk, and then we'll proceed. So here's the question. So we'll be thinking in terms of discrete subgroups of PSL2C for a lot of the talk, and then we'll try to generalize. So you have gamma. This is a geometrically infinite. This is font. This is the Kleinian group terminology, or distorted. This is the geometric group theory terminology. Subgroup of PSL2C equal to I sum plus of H3, distorted discrete subgroup. When is H contained in gamma geometrically finite, respectively undistorted? So the idea will be to start with, this question has has a certain amount of history. I'll say what the prototypical example is. So you start with a subgroup that is badly behaved with respect to the ambient metric in hyperbolic free space, or if you prefer to think in geometric group theory terms, think of a subgroup H sitting inside an ambient hyperbolic group G. And if you compare the word metric in the subgroup to the word metric in the big group, the first is more than linearly larger than the second metric. Okay? So that's the meaning of this word distorted. And undistorted means essentially that length function of H comparable to distance in H3. And okay, so here's the loose answer, and this is what we are going to try to make precise. The answer is very often. How often is the topic of this talk? Okay. So now let's look at So this is a meaningless statement. Yeah. So I'll put in all the clauses as we try to make this precise. For example, but that's not very often. That's rarely. Okay. So the subgroup is cyclic only rarely. Okay. So now let's make this statement more precise. And here's the example that started this whole thing off. This is due to Scott and Swaroop, probably 91 or 92. And here's, this is going to illustrate what we're talking about. So M is a closed hyperbolic free manifold fibering over the circle with fiber F. pi1f is n for normal. H contained in n is finitely generated and of infinite index, then H is geometrically finite. So this is a theorem. So that's the first example. And the second example, the second theorem, this is due to the canary. It's a consequence of a much more general theorem of his. M is a degenerate Kleinian surface group without, N is a degenerate Kleinian surface group without parabolics. H contained in F, finitely generated, and infinite index. This implies that H is geometrically finite. Okay, so I'll have to say a little bit about what this stuff means. There were these lectures by Kenichi Yoshika from last week so maybe a couple of weeks back. So let me just quickly recall what these words mean. So what's this? So if N contained in PSL2C is discrete, then you look at the limit set of N contained in C hat, which means basically you look at any point inside hyperbolic free space, look at its orbit under N, look at the collection of accumulation points on C hat. Take the convex hull of this limit set and look at convex hull of the limit set quotiented by, so the limit set is a minimal invariant subset of the Riemann sphere. So look at its convex hull, which means the smallest convex subset of hyperbolic free space, which has the same set as its set of accumulation points at infinity. Since lambda n is invariant under n, so is the convex hull, and so you take the quotient by n. This is called the convex core, and n is simply, respectively, doubly at degenerate if the convex, okay, so this guy has a name, so let's call this CC of n. If the convex core of n is homeomorphic to F cross closed interval 0 infinity, respectively, F cross minus infinity infinity. Okay, so so essentially what happens, in these cases where n is geometrically finite, the convex core looks like a surface cross minus 1, 1 compact. This is the, not S, F. So F is the surface. F is equal to, N is equal to pi1F. So the convex core is compact. So assume that F is a closed surface. So this is for F is closed. F cross minus 1, 1. This is a geometrically finite case. So you have your surface here. And then there are these, the boundary of the convex core. It's bounded by two pleated surfaces which have made their appearance earlier today. In the simply degenerate case, one side of the convex core pushes off to infinity. Okay? This goes off to infinity. This is the simply degenerate case. And the doubly degenerate case is where both sides go off to infinity. Okay? So this is the doubly degenerate case. So essentially, if you have a doubly degenerate case, then you have two ends. If you have if it's simply degenerate, then one side is bounded. There's a pleated surface here. But the other side goes off to infinity. This is the simply degenerate case. So I'll mostly talk about simply degenerate to reduce the exposition to one end. Okay? So these guys, places where you go off to infinity, these are called ends of the manifold. Okay? So, yeah. So the convex core, I mean, so essentially what does this mean? That, so what's an alternate way of thinking about degenerate guys? So let's fix a base reference surface, F equal to F naught. N is geometrically infinite, and that's essentially the same as saying it's either simply or doubly degenerate in the Kleinian group's case. What does this mean? This is the same thing as saying, so this is this whole non-compact part is the quotient of the convex core by the group. Yeah? Which means if you lift everything to the universal cover and you look at the convex hull of the limit set, equivalently you look at the convex hull of a lift of this surface F to the universal cover, you're going to get this whole non-compact region, which means effect is essentially that there exist closed geodesics exiting E plus. So alternately, you could think of this end as arbitrarily far, there are closed geodesics. Okay, so these are geodesics. This is gamma n, oh boy, this is really cluttered. Gamma n plus 1, and it goes off. Okay? So saying that the convex core goes off to infinity essentially says that if you try to join points here and you look at the geodesic representatives, you're going to have stuff going off infinity. Okay. So now what's both these examples. So how is this simply or doubly degenerate case related to the Scott-Swarup problem? What you do, again, so example of DD doubly degenerate groups. At some point of time, these groups used to be called totally degenerate. Anyway, so these examples of doubly degenerate groups come classically from these fibers of three manifolds fibering, the fiber subgroups of three manifolds fibering over the circle. So in Scott-Swarup example, let phi 1f equal to n. This is an example of something that's doubly degenerate. Why? Because all that you really need to prove in that case is that the convex core is all of surface cross minus infinity infinity, which means that if you lift to the universal cover, this whole surface cross minus infinity infinity lifts to all of hyperbolic free space. So what you want to prove is that the convex core is all of hyperbolic free space. What set can that be the convex hull of? it has to be the convex hull of the entire Riemann sphere. So what you want to prove for these fiber subgroups is that the limit set of a fiber subgroup is all of the Riemann sphere. But if you have a fiber subgroup like this, then n is normal in pi 1m. M is a closed hyperbolic three-manifold, so its fundamental group, so it has a compact fundamental domain, so that tessellates your entire hyperbolic three space. So the limit set of n, and you look at any element in your group pi 1m, so look at G lambda n G in, okay, so you look at lambda n acted upon by G. This is the same thing as the limit set of G times capital N, but you follow that up by some bounded length word, namely G inverse, Gn G inverse. Post multiplying by a fixed bounded length word does not change the limit set, but n is normal, so this is equal to lambda n. So what does this say? It says that the limit set of a normal subgroup is invariant under the whole group, right? So this implies that lambda n is invariant. It's a closed invariant subset of the Riemann sphere, invariant under all of gamma. Yeah? Which means this implies, but the limit set of any object is the smallest closed invariant subset. It's a fact. This is the same as lambda gamma, but gamma is a lattice, so this is the same as the Riemann sphere. Okay? So this is the explanation to say that these Scott-Swarup examples are examples of doubly degenerate groups, so we can put these two theorems in the same framework. Okay. So now let's try to get at, so now we are going to think about subgroups of this fiber group, yeah? And it really doesn't, I mean, you can specialize to one particular subgroup. So think of this, H is the fundamental group of this, and like many other people in geometric group theory and Kleinian groups, I'll keep confusing the subsurface and the subgroup it encodes. So the fundamental group of the subsurface is going to be denoted by H. I'll sometimes call the subsurface H by mistake. Please bear with me. Okay, so yeah, I've already done that. So the whole surface group is N, and the subsurface group is H, okay? And what are we trying to, so what is that question, what is the question that we are trying to address? Are these guys, so subgroups which correspond to subsurfaces of the distorted group, of the geometrically infinite group, are those geometrically finite or not? Yeah? And this very often essentially refers to any infinite index finitely generated subgroup of N. So very often means that H contained in N is finitely generated and infinite index. Yeah, so anything that has a chance of being geometrically finite is geometrically finite. That's really the content of that statement. Okay, so now we'll try to give an idea of what goes on, I mean, and we'll try to extend this phenomenon beyond this context of Kleinian groups, but let's try to understand a proof of this, which is probably going to be an overkill. The proof of Scott-Swarup and the proof of Dick Canary was, I mean, both of them were much simpler proofs. They use just one simple phenomenon, but there's actually quite a bit going on there. So let's try to expand on that. Okay. So we'll try to argue by contradiction. So suppose H, this is the subgroup of n, suppose H is not geometrically infinite. Okay? So then various things are going to happen. So lift, this is. So you look at the universal cover. This is F tilde, and unlike the usual picture of hyperbolic free space, which is drawn like a ball, I'll draw this one like a disk cross R. No, H is the subgroup, right? Is not geometrically finite. Thank you. Yeah, is not geometrically finite. Yes. Yeah. Suppose it. Yeah, it is geometrically. Suppose it is geometrically infinite. So F tilde, and you have this subgroup H contained in. Yeah. So H is contained in pi 1F, which is n. So F tilde is intrinsically, it's just the hyperbolic plane, and H has, H is it's an infinite index subgroup of pi 1F, so its limit set on the circle is some Cantor set. Okay? So lambda H1, this is the limit set of H in the circle at infinity, which is the same thing as, let's call this the boundary of n. Okay, so there are, there are two things that will be moving in between. One is stuff inside the boundary of the hyperbolic plane, and one is something in the boundary of the hyperbolic free space. Yeah, so I'll use superscripts 1 to indicate the context in which we are looking at the limit set. So suppose you have this guy, and then convex hull 1 of lambda H1. This is the convex hull in H2, identified as the universal cover of Rect. Okay, so if this guy is not geometrically finite, what will it mean? So you pick a base point. So there exists geodesic in H2 segments AN, BN, and I put an, oh boy, let's call it 1. Geodesic segments such that geodesics AN, BN 2, the geodesic in H3 joining AN, BN does not meet the n ball about your base point O. So what am I trying to say? You have inside the hyperbolic plane segments AN, BN. So these geodesic segments through O. Yeah? So they all pass through O. And what happens to the geodesic joining them in free space? It goes off and does not meet. So you look at this n ball. So this distance is n. This is a 3D ball. So you have geodesic segments of larger and larger length, such that if you look at the geodesic segment joining the endpoints, it does not pass through the n ball. Yeah. So basically, what are we trying to contradict? We're saying that, okay, so you have these geodesic segments in the subsurface, which are very far from geodesics in the ambient space. Yeah? This is just contradicting this. And so here's our So this implies pass to Gronov-Housdolff limit to get a collection of bi-infinite geodesics in H2. So what are you doing? You're taking all sequences, you look at collections of segments whose geodesic realization lies further and further away from the base point, yeah? And then you pass to all possible limits of these guys, yeah? By infinite geodesics. So this is an example of an algebraic lamination. So this is, it's a very crude topological construct that we are doing here, and it's really something that's coded by the group, so that's why we call them algebraic. Yeah? They will necessarily be geodesics in the convex hull, because what you're doing is you're looking at, so I mean, if you have a geodesic which goes past this, yeah? Well, for the time being, no, but really you're looking at segments contained in the subgroup itself. And in this particular case, since you're looking at a subgroup of a surface group, the subgroup is quasi-convex in the surface group. Yeah? So, yes, in this particular case, the answer is yes. But that's, yeah, I mean, this is a two-dimensional versus one-dimensional phenomenon. Yeah? We are interested in the three-dimensional phenomenon. Okay? And this gives a collection, yeah, okay, so collection of bi-infinite geodesics. And, well, make this H invariant. See, we had only elements passing through the origin, but for comfort, we'd like to, since we are working in the universal cover, we want our collection to be invariant under the subgroup, so make it H invariant by just translating it around by H, and you get a collection of pairs of points. So any bi-infinite geodesic contained in this convex hull has two endpoints in the convex hull, in the limit set of the subgroup in the big group, right? So any bi-infinite geodesic is quoted by a pair of points. So collection, so it gives you an H equivariant, H invariant collection of pairs of points P comma Q belonging to the limit set of H cross the limit set of H, and you remove from this the diagonal. Yeah? So pairs of distinct points out there, and it's invariant under H. And if you like, I mean, P comma Q is there, means Q comma P is also there, so it's invariant under this flip. Yeah? You can quotient out by the flip if you like, or not. I prefer not to quotient out by the flip, matter of taste. Okay, so these guys, so this collection has a name. So this collection, so what's the term in the title is algebraic laminations with ending thrown in as an afterthought. So what are algebraic laminations? I mean, they're just objects like this. They're pairs of points on the boundary of the group which are invariant under. It's a set which is closed, and okay, so for the timing, it's just a set contained in the boundary, cross boundary minus the diagonal, which is invariant under the group. Yeah. This collection is an example of an algebraic lamination, and we'll denote it as L sub Ct. What this stands for will make sense a little later. No. So this is just a purely algebraic stuff, and I mean, yeah, so we are addicted to surface groups, but essentially the same thing goes through for, say, free groups, yeah, where this notion of intersection in that very restrictive sense does not really make sense. It's just this, yeah. It's a very weak notion. All right, so that's this collection. This collection has some further property. Let's move here. So why have I mean, so I think you're going to have a glut of laminations in this lecture. So these are some examples. I mean, we're going to get back to other standard laminations. All right. So, okay. So let's get back to this picture. You have this AN and BN, yeah? And you have a geodesic joining them which lies outside a large ball, yeah? Which means, so if AN, BN, geodesic 2, which means that the geodesic realization in hyperbolic 3 space intersects the ball around O in the empty set, this implies, it's actually more or less equivalent to, visual diameter of this pair of points, AN, BN, in H3, based at O, is e power minus n. So recall that we had taken in the first week, we had tried to construct a metric on the boundary of any hyperbolic group. In particular, say, for example, hyperbolic 3 space is an example of hyperbolic space. So you thought of some things like the Gromov inner product, and you essentially e power minus the Gromov inner product was the visual metric, and the visual diameter just means the metric in the just means the diameter in the visual metric. Yeah. So if the geodesic joining a pair of points lies outside a very large ball, it subtends a very small angle at your eye at the base point. This exact number is not important. What's important is that it goes to 0 as that quantity going to 0 is the same as this quantity going to infinity. Okay, so this implies, this is a moral implication. Well, I won't write that. This is on yeah. This implies that if you pass to a limit, A infinity, B infinity, so the visual diameter is shrinking to 0, has visual diameter 0. But A infinity and B infinity are points at infinity, right? Now they are points at infinity of hyperbolic 3 space, right? We were taking geodesics in hyperbolic 3 space and we were passing to a limit. What does it mean to say that a set has visual diameter 0? It just means, it would mean that, I mean, now this is a set at infinity, this is contained in C hat, it basically says that A infinity is equal to infinity, right? Well, this is only morally true, and this requires, essentially, that you have passed from A and B, and from the sequence in the subgroup, you've extended this whole thing to the boundary at infinity, and this is well, let's call this a hope. This is true. Yeah, this is true if the inclusion of f tilde into H3 extends continuously to I hat from F tilde union the boundary of F tilde, which is the circle at infinity, to H3 union C hat, which is the boundary of H3. Yeah? So if there is a continuous extension like this, then this is exactly true. Yeah? So such continuous extensions have a name. So these guys are called Thurston maps. And this is the C and this is the T in LCT. Yeah? So you look at pass to Gronov-Housdolff limit to get a collection of bi-infinite geodesics in H2, make H invariant, and this H invariant collection of pairs of points. This is an example of an algebraic lamination. And so now let's give a formal definition of this gadget. So what's LCT? Running out of board space even with so much space. Okay, so what do you have here? H is contained in H dot O, an orbit is contained in H3. This has a CT map. Suppose, then LCT, this is equal to P comma Q belonging to boundary H cross boundary H minus delta, such that I hat P is equal to I hat Q. Yeah. So it's pairs of points. So suppose there exists a Cannon-Thurston map. Then this Cannon-Thurston lamination is pairs of points on the boundary which get identified under the Cannon-Thurston. So point preimages when the point preimage has more than one point. Yeah? So fact, this is the lemma. H is geometrically finite if and only if this lamination is empty. Okay? So that's not, it's fairly easy to see. Yeah? Both directions are fairly easy to see. If I'm provided, there's a crucial hypothesis. Hypothesis is, suppose H contained in G or H3 has a CT map, then this characterizes, so the geometric finiteness is characterized by this CT lamination being empty. So what is this CT lamination, the Cannon-Thurston lamination, really capturing? It's capturing sets of bi-infinite geodesics whose geodesic realization is infinitely far away, which essentially says that the 2 points at the end are getting identified. Now let's get back to, I think this picture has served its purpose. Now let's get to most standard notions of laminations. And I've erased the picture I need. No, suppose H is not geometrically finite. I have gotten, I mean, this one was, I'm not proving anything. I'm saying that this one is an example of an algebraic lamination. One is the CT lamination. Yeah? So we'll come to the second collection of. So again, suppose H is not geometrically finite, it's going to carry on, but we are going to get something, some other set of laminations. Not geometrically finite. Okay, so again, so suppose you have this simply degenerate end. What do you do? So consider sequences gamma n exiting E. So this is my end E, and you have these closed geodesics which exit the end. Okay? So now these are geodesic realizations inside the three-manifold. So, well, look at alpha n contained in, so this was my surface F, freely homotopic to gamma n, such that alpha n is a closed geodesic in F with respect to its intrinsic metric. Yeah. So F is a hyperbolic surface. Yeah. So this is a, think of F as intrinsically it's just some hyperbolic surface. So what are you doing? You're taking this guy and you're flowing it back. Who knows what it looks like? Might intersect itself. I'm hoping to sufficiently muddle it up. Okay. All right. So you have some closed geodesic on the surface with respect to its intrinsic metric. And this guy is freely homotopic inside the three-manifold to gamma n. Yeah? This guy is called alpha n. Now, alpha n tilde, these are lifts of alpha n to H2, identified with the universal cover. And so, okay, so this is a lift of alpha n to H2, passing through fixed fundamental domain. So you see that we had made a choice of a base point there. Yeah, I mean, essentially, instead of a base point, we could choose a fuzzy base point, essentially called a fundamental domain, and you look at your geodesic here, whose geodesic realization is far away, and you make it pass through that fundamental domain. This is now a bi-infinite geodesic, has endpoints alpha n tilde plus, alpha n tilde minus. So this is a bi-infinite geodesic. Again, it can be ordered by a pair of points on the circle at infinity. Again, pass to Gronov-Housdolff limit and make, oh boy. Yeah, that's okay. Pass to Gronov-Housdolff limit and make, I want to, H is not freely homotopic to gamma n, which is an element of H. Yeah, so it's, yeah. So these are, so look at alpha n contained in F, freely homotopic to gamma n, belonging to alpha n, contained in subsurface H. Yeah, so this is the confusion that I was trying to avoid. So essentially, you have your, okay, let's erase this and make a nicer picture. So you have your surface F, and contained inside this subsurface, you have this subsurface, and inside that subsurface, this gamma n is freely homotopic to some curve that goes around. Okay, this is my alpha n. Okay, so all this is happening with the hypothesis that H is not geometrically finite. That means there are closed loops on that subsurface whose geodesic realizations exit the end. Yeah? Pass to Gronov-Housdolff limit and make H invariant And this is again a collection of laminations, but this is a purely topological construct. Yeah? So because we are just passing to, okay, so in fact here we can actually forget Gromov from here. We can just pass to the Housdolff limit. Housdolff limit on closed subsets of this fiber F. So Gromov-Housdolff is adapted to non-compact gadgets. So you just look at limits on this compact set F, and you pass to limits, and you're going to get, so you're going to get some collection of bi-infinite geodesics. So this is LAEL, because this is a purely topological construct, and you're going to get a new lamination, LAEL. Okay? All right. So that's a new lamination. But what's the difference between the previous construct and this one? In the previous, you were considering geodesic segments and looking at geodesic realizations. What you're looking at now are closed loops whose geodesic realization is very far away. So from segments to loops. But the process of constructing them is the same. You pass to limits, pass to Housdolff limits. Okay? You take all limits. You take all limits, you make it H invariant. Yeah. Free. And this is really, this is Thurston's ending lamination. So look at, now this is a crucial hypothesis. Simple closed curves alpha n on F whose geodesic realization gamma n exits E. Yeah? Whose geodesic realizations exit E. Yeah. So we are trying to specialize this further. Instead of looking at arbitrary closed geodesics on the surface whose geodesic realizations are far away and then just taking Housdolff limits, you're now looking at simple closed curves. Yeah? So the point of that diagram was that the curve alpha n need not be closed, need not be simple. It could be self-intersecting. So look at simple closed curves, gamma n exit E, and this implies that alpha n converge to a unique geodesic lamination. So this is in Thurston's notes. Unique geodesic lamination LEL. So this is LAEL and this is LEL. In the space of projectivized measured laminations on S. So measured laminations have already been talked about many times, so I won't say what it is. You just look at all measured laminations with positive coefficients and projectivize them. Yeah? So assume that all of them have weight 1. Yeah? What's important here is that independent, I mean, so this is really the crucial part of it. Essentially, it says that you look at any sequence of closed geodesics in the 3-manifold corresponding to simple closed geodesics on the surface. Independent of what choices you made, they always converge to a unique geodesic lamination in the projectivized measured lamination space. How are you looking at these simple closed curves as elements of PMLS? You weight every simple closed curve by the weight 1. Yeah? So then it's a lamination of weight 1. And then you look at limits in this PMLS space. The third kind of lamination. We're almost there. One more candidate. But you've already seen this in some other form already. maybe towards the end of last week. Okay. So, okay. So what are we going to do? Look at now gamma n exiting E. Yeah. Translate back to alpha n contained in F tilde, and look at and consider limit F tilde dh was the hyperbolic metric divided by the length of alpha n. So you look at F tilde, which is identified with H2, and you scale the metric there by doing what? You look at closed geodesics which exit the end, look at a free homotopy representative on the surface. This is alpha n, and here's the basic fact about hyperbolic geometry. If the geodesic realization is outside, and it's the distance from the base surface, suppose this is something like n, and this is, say, order 1, the length of, if this is n and this is order 1, this is, okay, let's give a name. So this is, say, some L. So length of alpha n is something like L e power n. So if there's a geodesic of length 1, and you move a distance n from it, then the closed geodesic outside an n ball grows exponentially. Yeah, so that's what it is. So what we are doing here is we are looking at this hyperbolic metric, and we are scaling it by some huge number. Yeah, so this is something like e power n. So in Mike's lectures on Friday, you had that this collection converges to some R tree with some. So the spaces, okay, so there's another way of thinking about it. Hyperbolic space is Gromov hyperbolic with some fixed delta. When you scale the metric, it becomes delta divided by some large number, hyperbolic. So in the limit, it's this number is going to go to 0. So you're going to get a 0 hyperbolic metric space. 0 hyperbolic metric spaces are the same thing as saying that the space is an R tree. Yeah, that's an equivalent way. What does it mean? From definition, it says that you take a triangle ABC. AB lies in the 0 neighborhood of AC union BC. Yeah? So it means that triangles look like this. This is A, B, C. BC lies in the neighborhood of the 0 neighborhood of the union of the other two. So this is an R tree. Yeah. And consider G infinity. Okay, so G power minus infinity, G power infinity, contained in boundary of H2 cross boundary of H2 minus the diagonal, such that the translation length, so I think tau dr of G is less than epsilon. Yeah. So this is, so you look at all pairs of points on the boundary such that the element that you have translates by less than epsilon in this R tree. Yeah. Again, pass to limits, and this gives you a new lamination, call it LR. Okay, so now we've put all the laminations there, and I just have 15 minutes left. So there are 4 laminations here, in this very crude sense. There's this, the CT laminations which come from Cannon-Thurston maps, and the criterion for proving quasi-convexity really comes from there. We want to prove that a certain lamination is empty. Yeah. But okay, so here's a fact. So during the rest of the talk, what I'll try to do is essentially, yes? Alpha n? No, alpha n is just a sequence whose geodesic realizations exit the end. Yeah? Yeah? That, yeah, I hate ultra filters. Okay, so here, I mean, this is a nice constructive sequence, yes? I mean, we don't want to say that it depends on the axiom of choice, etc., etc. So, okay, so here I think really what's going on is what did we do in the previous cases? We are really, I mean, that alpha and the choice, in order to prove that it's the same thing as something else, you're going to use that kind of stuff. Yeah? That's really the reason. Apart from a personal, irrational prejudice about the axiom of choice. Okay. Yeah, you'd get the same thing. You'd get the same thing, but I don't want to vouch for that. Okay? So, yeah. Because in all reasonable cases, it does not depend on this ultrafilter. It's just a sequence. I mean, it's actual convergence on the nose in all civilized cases. Okay, so what's the strategy? So we want to prove that H is quasi-convex. Yeah? So quasi-convexity the relevant lamination is LCT. Yeah? Now, what about laminations? I mean, so the Thurston, yeah, so let's try this. So property of LEL, this is the Thurston ending lamination. This is something that is irrational, minimal, filling, etc., etc. It's got all kinds of lovely properties. There's a certain strong property that means that no leaf of LEL is carried by any H contained in N. What does that mean? If you look at the Thurston ending laminations, any leaf, the closure of it is the whole thing. It's a minimal lamination. Yeah? And each leaf is filling. So in the complement of any leaf, there are, I mean, any complementary part of the lamination these are all simply connected. So which basically, you can soup that up a little more. Essentially says that no leaf of this Thurston ending lamination has pairs of endpoints or even a single endpoint on the limit set of H contained in the circle. So this we should think of as a mixing property of LEL. So there's no subgroup which contains anything. So which means what? If you combine this with so what would we like to say? So we want LCT equal to LEL. If we can prove that, I mean, suppose we can prove that these two things are the same, then what would follow is that no leaf of the Cannon-Thurston lamination is carried by a subgroup of infinite index, finitely generated. So this implies that, I think this has a name, is carried by any age. This is called strongly irrational. Instead of having geometric subsurfaces, you just say any finitely generated infinite index subgroup. So such laminations are called strongly irrational. So what if we have this? This implies that no leaf of LCT is carried by H, which means its pair of points on the boundary of H cannot code a leaf of the CT lamination. This implies, by that lemma which I had written there, it's quasi-convex, geometrically finite. These are all interchangeable terms. It's used more in symmetric group theory, it's used more in Klein groups. So this is what we want. Yeah? Okay. And this is really an overkill. Oh, I should have mentioned this right at the beginning. So all this is joint work with Kasra. Okay? Yeah. Sorry. Okay. All right, so here's this fact. So this is in the Kleinian groups world theorem. Essentially says that for n simply or doubly degenerate, LEL, this is the Thurston ending lamination. Let's put this dia here means LEL union diagonals. This is equal to LCT. Okay? So there's a general theorem which essentially says that when you have one of these simply or doubly degenerate groups, then the diagonal closure of ending lamination, which means essentially you look at all the complementary ideal polygons of the ending lamination and you throw in all possible diagonals, that's a diagonal closure, that's exactly equal to this LCT. So these two things together, this implies quasi-convexity of H. Okay. So we've given a pretty, so this theorem takes a fair bit of, So this is really an overkill. Dick Canary's proof was much simpler. It used much less machinery. But this is a proof that generalizes to a considerably more general setting, and that's what we are going to try to say in the last few minutes. So suppose n is hyperbolic, G is hyperbolic. Now we are moving to the geometric group theory world. So n is normal in G. And this is an old theorem in this context. Essentially says that the LAEL, this is the same as LCT. Yeah? So remember that, we were looking at closed geodesics exiting the end. Yeah? And then we were getting sub-algebraic ending lamination out of that. So in the particular context, when you have a hyperbolic normal subgroup of a hyperbolic group G, yeah, it's true that the algebraic ending lamination that you get from just closed curves exiting the end That's the same as this Cannon-Thurston lamination. So what do we have left to do? And so here, in the general case of a hyperbolic normal subgroup of a hyperbolic group, we do not have the luxury of having a space like projectivized measured lamination space. Yeah? So do not have PMLS here. Okay? So this is really why I was insisting about forgetting stuff intersects each other. What do we have? Do have this real tree interpretation. Yeah? So you have, I mean, what you're doing is when we defined the real tree ending lamination, what did we do? We took a fixed Gromov hyperbolic space, the universal cover of the surface, and we kept scaling it. In the limit, we got an R tree, and we just looked at elements which have translation length 0 on it. Okay? Well, translation length smaller and smaller and pass to the limit. Yeah? So we can't, in the Thurston picture, the Thurston ending lamination and this real tree ending lamination, they're essentially the same object. That's not entirely, requires quite a bit of work, but essentially they capture the same amount of information. But something that we can do in this particular case. In the general case, and I won't look at surface groups anymore. So, well, maybe I will. So, so for, how much time do I have? I have 3 minutes. For n, a free group on n generators, and so what we have, 1 going to Fn, going to G, going to Q, going to 1. This is hyperbolic. These groups Q are nowadays called, well, not nowadays, I mean, for almost a decade, these guys are what are called convex co-compact subgroups, and there's a whole bunch of names I should put here. Bob, Moshe, Kent, Ansel, Ammenstadt. Yeah, so Q is an example of a convex co-compact group. It's a theory which has been extensively developed for subgroups of mapping class groups, and so this guy is contained in the outer automorphism group of a free group. And so what does, so for G hyperbolic, yeah, so here's the hypothesis, theorem, and this is by, suppose Q is, I think independently, this is also by Spencer Dodell and Sam Taylor. The proofs are, I mean, quite different proofs. So suppose Q is a convex co-compact subgroup of out Fn, which essentially means that Q is, there's an issue about the definition. I think I'm using their definition here, along with Ilya Kapovich. So Q is purely hyperbolic automorphisms and admits quasi-convex orbit in a certain three-factor complex. I mean, there's a certain hyperbolic complex associated with this. And H contained in Fn is finitely generated, infinite index, this implies that H contained in G is quasi-convex. And this is same, okay, I won't write this, let me just say this here. So there's one crucial ingredient missing from the proof I've sketched. I said that we'll need to get around the fact that we don't have these Thurston ending laminations. We have only the real laminations, the real tree laminations there. And here's a theorem which allows us to do this. This is by Spencer Doder, Ilya Kapovich, and Sam Taylor, which says that the real tree lamination, this is the same thing as the algebraic ending lamination. Yeah. Then, again, so now you quote a bunch of theorems. This is again, the boundary was identified by Ursula and by Vesvina and Patrick Reynolds, the boundary of this space which I have just used without defining. Vesvina Reynolds, if you don't know what that is, forget it. And this is, just take this theorem as a black box, essentially says that LR has this mixing property. So there are two papers, so Reynolds, and I'll put Reynolds again because there are two papers of Patrick Reynolds that are used here. LR, or these are strongly irrational. Yeah. So again, so by this old theorem of mine, this is equal to LCT. So LCT is equal to the algebraic ending laminations. And these three guys prove that that's equal to the R3 lamination. Patrick Reynolds proves that these are all strongly irrational. And this implies that LCT is strongly irrational. That implies that theorem there. Yeah. And same works for Fn replaced by Phi1S, where S is hyperbolic, possibly non-compact. And I should say here, Spencer, Chris, Autumn Kent, and Chris Leininger. This was the compact case. And so yeah, I'll stop there. So essentially, if the normal subgroup is either a free group or the fundamental group of a closed surface or a fundamental group of a surface with a puncture, you have all these generalizations of the Scott's group. Thank you.
So is there some, can this distortion be quantified, and is there some kind of quantified version?
Yeah, this is a very good question. I wanted to make the statement right at the beginning. So essentially what is the, so what does this say? I mean, one way of thinking about it is that the laminations pick out a certain extrinsic geometry of the subgroup by picking out exactly the bi-infinite directions which are most distorted. So all bi-infinite directions which are distorted are captured by these laminations. Yeah, so essentially, yeah, that's what allows you to this. If it's realized far away, it's exponentially distorted, and it says that these are only the directions. And those directions are captured. I mean, to make that precise, you want some kind of asymptotic extrinsic geometry that's furnished by the Scannon-Thurston map. by pairs of points getting identified together. And you play these off against each other. Yeah.
Okay, let's thank the speaker again.